filled out that chart, just go ahead and continue to do that, and I'll be right there with you. Okay, I think it actually started working. Okay, so for something like this, remember, you don't want to just have to type in 2.9 over and over again for x into the home screen. So it was pretty easy with x squared, but for something like this, you're going to want to use your calculator's y equals option, because it allows you to store a function that you're going to use over and over and over again. So in this case, because you have a horizontal division bar, get in the practice of using that as well. So that's alpha y equals. And Santi, you're just going to have to put your numerator and denominator in parentheses, or you got one of those, or this one. Okay. So if you don't have the math print, if you have like an 83 or something, just put the numerator in parentheses and hit divided by and put the denominator in parentheses. Okay. But if you have math print, then alpha y equals unlocks n over d, and then you have the horizontal division bar. So then it's just x cubed. Click to the right, 3x squared. You have to use calculator syntax for the x. Oh, I did forget the minus. Thank you. Yeah, so if you want to insert something, go to where you want to insert it, and second delete gives you the insert command. Thank you. Good eye. All right, so there it is. It's in Y1. You kind of double check before you kind of leave, and it looks okay now. So then you go to the home screen, which is second mode. That quits. Get you back to the home screen. So now to fill in the chart, again, to get to the y's, the math print shortcut is alpha trace, and it's default highlighted for 1. So then you open parentheses, you type in 2.9, hit enter, and boom, there it is. Now, if you don't have math print, you can still get to the y equals. You just have to hit the vars button, which is, just to the left of clear. And then you click to the right to y vars. That means y variables. And then it's on function. So if you hit enter, there's all of them. So it's vars, y vars, function. Vars, which means variables, y variables, and then your function variables. And you can still get to it that way. So then it allows you just to keep open parentheses and type them in. So it's a lot faster, 2.99. So go ahead and do that this way if you haven't done it yet. Blah, blah, blah. And remember, how many decimals do we report? 3, right? Whether we round or truncate, it's up to us. Round or truncate. Okay, so fast forward. Maybe you're not done. Did you get a little deja vu finishing out the chart from yesterday? Yesterday we have these values here for x squared. And if you do it correctly, you should actually get the exact same values for this function as we did for the other one, the exact same. Okay? So if we were to then just use the data, because I haven't hit graph yet, and I don't want to do that because that kind of gives it away. But if we just use the data again, it says, what do these values tell you about the function values, the y values, in the neighborhood of 3? This Scorpion. Will do. Anna, you are checking out. Yeah. So in the neighborhood of 3, if you notice here again, as x approaches 3 from the left, the y values look like they're approaching 9 again. And similarly over here, 3.1, 3.01, as x approaches 3 from the right, it appears that the y values are decreasing towards 9 again. So we could say the exact same thing. It appears that the y values approach 9. Have a good appointment. Approach, there we go, 9. All right, and now, just using the data, based on the chart and the data alone, what would you suspect the actual value then of the function at 3 to be? Well, based on the data, again, you would be foolish to think it's anything other than 9, right? As you get closer and closer to 3 from both sides, the y value is getting really, really close to 9, so maybe at 3 it is 9. But then what is g of 3? Well, to figure out the actual value, we can plug it in here. So you could do that on your calculator, or you could plug it into your head. But look at the denominator. What happens when you plug a 3 into the denominator? You get 0, right? And so division by 0 is non-existent. So what is the actual value of g of 3? It's DNE. It doesn't exist. If you tried plugging it in, you'd hit alpha trace number 1, and then at 3. It's going to give you division by 0 error. Okay? So the function value doesn't exist. Ah, okay. Is there still a way to mathematically communicate then? Because now there's nothing going on at 3. Is there a mathematical way to communicate the result from the chart above? And the answer is yes. So here's the notation again. We can still say that while g of 3 equals dne doesn't exist, the limit, LIM, and underneath there, remember we put x arrow 3, and then if you put the little negative exponent thing of g of x, that means you're approaching 3 from the left. It's 9. And similarly, the limit as x approaches 3 from the right-hand side of g of x is also 9. So the limit is this notion of motion, and it makes no claim about actually reaching a destination. It's just getting closer and closer and closer to something and looking to see what the y values are. Okay. Now, what does that tell us about the graph of the function then at x equals 3? We know it doesn't exist, so there's an interruption in the graph. We know it's a discontinuity, right? The graph lives to the left and right. Can you use this information to decipher what type of discontinuity it is? A what? Well, if I plug in a 3, I get dne, so I know the graph doesn't exist there. But oh yeah, to find it you could, but based upon this, let's see what we have here. Let's decipher this, right? So that means that here we are at x equals 3, and we know the graph was doing something like this. It was increasing towards y equals 9 from one side, and it was decreasing towards y equals 9 from the other side. So as I got closer and closer to 3, the y values were getting closer and closer to 9, but at 3, the function didn't exist, right? That pretty much graphically summarizes what we just said above with math language. What type of discontinuity is that? That's a removable point discontinuity. Yeah, it's a removable point discontinuity. Also known as a what? A hole. Yeah. And you can call it a hole. So that function has a hole at what point? 3, 9. Yeah. The limit value from both sides that we snuck up on, it's not the y value of the function value, it's the y value of the hole. Okay? And so the limit still gives you a way to talk about the y values at a place, especially useful, where the function value doesn't exist. Yeah. Now, if you want to see what the graph looks like, just hit zoom 6. That's your standard viewing window. It's taking a while. There it is. It's coming in. Wow, it looks a whole heck of a lot like what familiar function? It looks a whole lot like x squared. What's the value of x squared at 3? 9. Okay. So the question is then, is there a way to figure that out without doing all these tedious calculations? With the calculator, it's not that bad, right? But imagine in the day before calculators, computing that would be really, really ugly. So the answer is absolutely yes. There's an algebraic way to do it, and Santiago, you were kind of already on that. But before we do that, that's the next example. Going where we can't go, right? Where's one of the places that we're not allowed to go? Area 51. Anyone ever been there? If you're here today, you haven't been there, because if you go, you die. Why? It says the use of deadly force, right? They'll kill you if you go there, right? And you try to insist that you want in. Because that's where they keep all the alien technology and the aliens, right? So you can't go there. But because you can't go there, this is an aerial view. There's like barbed wire fence, and it's electrified. You have like foothills and stuff all around there, but you have people that are always like coming up there to try and see it, right? They're coming in. They're trying to catch a view of the aliens. But they get as close to the fence as they can to kind of peek in. And how close to the fence can you actually get without touching the fence? If you touch the fence, you get zapped. So how close can you get to the fence without actually getting there? Very good. That's the perfect answer. You can get infinitely close to the fence without touching it. Okay? Simply by saying, okay, if I'm a foot away from the fence, I'm always going to half my distance to the fence. So if I'm a foot away, I'm going to move 6 inches towards the fence, right? And now I'm 6 inches away, so I'm going to split that distance. I'm going to go 3 more inches. Now I'm 3 inches from the fence. I'm going to split that. Now I'm 1.5 inches away. I'm going to split that. I'm 0.75, so on and so forth. If you keep halving your distance to the fence, Will you ever get to the fence? No, you won't. And you could do it forever and ever and ever, okay? So you can get infinitely close to the fence. So that's kind of the idea of the limit. It makes no claim about actually getting to the point. You could say this whole thing is the ordered pair, the dot on the graph. Instead, it gets as close as you'd like to that point and peers into that section to kind of see what's going on, all right? So that's what the limit does. It allows us to go where we don't go, or where we can't go. So keep in mind all along that the limit is a notion or an idea of motion. So when we talk about a limit, we talk about approaching an x value and looking to see what the y values do. We are approaching a y value. In that case, you could think of like the graph. You could think of the graph as a road that you're driving on, right? When you drive on the road, you're approaching your destination, right? So think of the graph as roads upon which we can drive. And then think of the function value as being the location of like a canyon or something, or a chasm, or some giant hole in the ground, right? If you were driving with your family or loved ones in an automobile, is that right? Automobile? No. In a car. And there were no ramps to jump across like the Duke boys. This might be what it looks like, right? You have this canyon right here, and you have this road coming in from the left, and you have this road that's going out on the right. And those two roads appear to be lining up. But notice, you wouldn't want to drive across right now, would you? Right, because you'd go right in, right? Unless that was your intention. But then, come see me. I have someone for you to talk to. Okay. We need what still to drive across? That's missing. Safely. We need the bridge, right? Okay. So the bridge is going to be synonymous. There we go. The bridge is going to actually be the point. Okay. It's the point. That's 3, 9. Whereas the road on either side, this is going to be the limit from either side. The reason we're doing this and talking about safely driving across is because we are really secretly interested in a continuous function. And we want to be able to talk about what makes a function continuous. A function is continuous if you could just draw it from left to right without lifting your pen or pencil, right? But that's not a very rigorous definition. So using the limit and the function value, we can come up with an idea. If the goal is to cross the bridge safely, here's what I would need. I would need 3 things. I would need a road coming in to a particular point. Or that is, I would need a limit from the left coming into a particular y value. It would then need to be connected to the bridge at that point. Or there would need to be an ordered pair that has the same y value at that point. And then there would be a road that was connected to the point on the other side leading out from it. Or the limit from the right would be the same y value as the point. Okay? And only if the road coming in and the bridge and the road going out are all connected at the same y value will that be continuous and safe to drive across. If any one of those 3 things are missing, right, or if any 2 of them are not at the same y value, we can't safely drive across, okay? And so the limits give us a way to rigorously define what it means for a function to be continuous at a point, okay? So we'll summarize that here in a little bit. All right, so now back to example 4. Or back to example 4, which is the same function we just worked with the calculator. It's the one we're staring at right there. Which, by the way, if you're in the graph mode and you hit trace, if you plug in a 3, it's going to give you y equals nothing, okay? Because your calculator is kind of drawing the discontinuity to scale, which is infinitely thin, so you're not going to see it on there. All right, it says, how can we algebraically determine the removable point discontinuity from here, okay? Well, here's what we're going to be doing anytime we have a function, right? Let's look at g of x. We're going to look at the domain first. We should always kind of get in the habit of analyzing that on our own. We don't want to divide by 0. We don't want to take square roots of negatives, and we don't want to take logs of anything that's positive. So really the only risk here is division by 0. And what value of x causes 0 in the denominator? 3, right? So I know the domain of g. That's how you write it, d sub g colon. It's going to be the set of all x such that x is not 3. And now we're really curious. Okay, if the graph or the function doesn't exist at 3, but it lives to the left of 3 and to the right of 3, that is a discontinuity. I want to know what's going on in the neighborhood of 3. I can't just plug a 3 in to figure out the y values, but I want to figure it out another way. So we just did it numerically. We're going to figure it out graphically. Okay, so let's go ahead and factor this. We're going to factor g of x, and this is going to be a typical thing to do. We got a polynomial over a polynomial. So what's the first rule of factoring? Yeah, look for a common factor. And in the top, it looks like there's an x squared that's common. So if we factor out an x squared, we're left with x minus 3. And at the bottom, we're left with x minus 3. Now, this one is pretty easy. If you plug a 3 in, again, we know it's not going to work. When you plug a 3 in, you get 0 in the denominator. But what are you going to get in the numerator as well? You're also going to get a 0, right? So whenever you have a polynomial divided by a polynomial, we call that a rational function. Anytime you get 0 over 0, there's going to be a hole. Every time. Okay? So we know there's a hole there. So we know the graph is going to look like, if you divide out those factors that were causing 0 over 0, if you divide those out, that means that g of x is going to take on the same physical appearance as whatever equation is left, which is just x squared, right? Except that x equals 3. So the only difference then between g of x and the graph of x squared is that x equals 3, where g of x has a hole and x squared does not, okay? And that's why when we graphed our function g of x, it looked just like x squared. But now how can we use this fact to help us find the y value of the hole that used to be there before someone removed it? Swiper, perhaps? You plug it back in. Yeah, if the only difference between g and x squared is that g has a hole and x squared doesn't, x squared paves right over where the hole was. So you can use the y value of x squared to figure out the y value of the hole, okay? So really, you just plug it right back in. And 3 squared is equal to 9. Okay, so we did that in pre-cal. So we could say now, so g has a hole at the point 3, 9. All right, so really all we did is we factored, divided out, and then we plugged in that value into what was left to get the y value of the hole. And the only difference now is we're saying then we can define this a little bit differently. Because we know there's a hole there and the y value is 9, we could say then that we could say the limit, where do we do that up here? We could say this. Because we know now what the y value of the hole is,
teachers, please have
we can say this.
Please check your emails at this time. If you have a student in your room that is on the list emailed to you by Carrie Highland and they do not have their iPads, please send them to the Commons at this time. We are trying to get the iPads out to students as quickly as possible. Thank you.
Who still does not have an iPad? You, 3, 4, 5, 6, 7. No? Okay. Oof. All right. Real quickly, the point I was trying to make is, yes, there is a way to find the y value of the hole. And once you know the y value of the hole, you know the value of the limit from both sides. So that prevents you from having to tediously sneak up on it to figure out the y values from both sides. Okay? So here's an important theorem, and then I'll kind of set you loose on number 5 while I check the email. Okay, this is called the general limit theorem. Anything that's in the box is pretty important. The general limit theorem. And it's an if and only if theorem. So if you ever see this double-headed arrow, it means if and only if, which means the left side implies the right, and the right side equally implies the left. So you could say if then, starting on either side. So here's what it says. If the limit as x approaches some arbitrary value of x, we'll call it c. C is just any number. If we approach that number from the left of the function and it equals L, where L is just any finite number, and that happens to also equal the limit from the right-hand side, okay? That is if the roads are lining up. If the road coming in from the left is lining up with the road coming from the right, then we say the limit exists and it equals L. And notice the difference here. There's no plus or minus written by it. That's called the general limit. That is the general limit. If you don't see the plus or minus, it's the general limit. So basically we're saying if it approaches the same thing from the left and right, we could say the general limit exists. And it's the same y value. But it also works in reverse. If you were told that the general limit is equal to a number, then you know it's approaching that same y value from both the left and the right-hand sides. Now, if that's not the case, here's the upshot of that. If that's not the case, then the general limit wouldn't exist. If the limit from the left and the right are both different numbers, then the general limit's not going to exist. Or if the limit from the left and the right don't exist themselves, then the general limit's not going to exist. Now, there's only two cases where that's going to be true, okay? The general limit will exist in only one of two cases, and I'll do it graphically. Let's call this x equals c. The function can come in like this, and at c you have like a hole. There could be a hole there. Or it could be something that looks like this. And you actually have a continuous function there. Those are the only two instances graphically where the limit will exist, because those are the only two where if you approach from the left and the right side, you're approaching the exact same y value, okay? So notice the general limit can exist independently of what the function value is, right? Whether there's a bridge or not a bridge, who cares? If the roads are lining up, pointing to the same y value, the general limit will exist, okay? All right, try to do example 5. It says algebraically determine the following. What I would recommend is to factor that first and find the domain. Anything that divides out is going to be the location of the hole, and the y value of the hole is going to be the limit at that point. So see if you can answer A, B, C, and D, and then I'll check that email real quick. Taylor, you're on the list if you want to go. No. There's a small list here. That's it. Okay. All right, let's see how y'all are doing here. We have a quadratic divided by a quadratic, so that's a polynomial over a polynomial. We call those rational functions. Okay? So anytime you have a rational function, you might have discontinuities at any values that make the denominator 0. They're either going to be wholes or vertical asymptotes each and every time. It says to algebraically determine the following function values, limit values. So what you might want to do is just factor it first, because factoring tells you a lot of information. So if you factor the top, it looks like it's x plus 3, x plus 1. And if you factor the bottom, it looks like it's x minus 4 times x plus 1. Okay, so that's very, very useful, because before we can answer any questions, we'll know something about the function. The domain, or you could say d sub f if you want, it's going to be the set of all x such that x is not equal to what two values? 4 and negative 1. Yeah, you don't have to set that equal to 0 and set them each equal to 0 and solve algebraically. Just look at it. X minus 4, when you plug in a 4, you get 0 and negative 1. So you could say negative 1 comma 4 or 4 comma negative 1. All right, so both of those guys are not in the domain. Both of those guys are discontinuities. All right, so now what type are they? Well, let's see. The x plus 1 factor divides out. We can remove it from the equation, so it's going to be a whole, a removable point discontinuity. If you can remove it from the equation, it's removable. If you plugged in a negative 1 to the top and bottom, you get 0 over 0. Okay, so we can go ahead and say that f has a whole at, and we can list it as an ordered pair, negative 1 comma, and then how do we figure the y value of the whole? What do we just do? We plugged it back into everything that's left after you divide out the whole, which is your x plus 3, x minus 4. So when you plug it into x plus 3 over x minus 4, you get 3 minus 1 is 2 over negative 5. 2 over negative 5, so that's negative 2/5. Okay? That is the y value of the whole. Now, the other value that gives you 0 in the denominator is 4. Can you remove the x minus 4 factor from the equation? Nope, you can't. And so it's a non-removable infinite discontinuity, also known as a vertical asymptote. Or if you plug a 4 into the top, you get 7 over 0. And remember, non-zero over 0 means vertical asymptote. So we could then say that f has a vertical asymptote, VA, you can abbreviate it, at, and then you say x equals. Now let's see if we can use that information to answer the questions. Part A, what is f of negative 1? And when I say f of negative 1, that is the y value. That is the point. That is the bridge analogy that we've been making. When you plug a negative 1 in here, what do you get as an output? You get 0 over 0, right? And when you get a 0 in the denominator, it's game over for point. It's game over for function value. The function value will not exist. It's not in the domain, remember. So the function value is DNE, or non-existent. Okay? And that's why we're learning this idea of the limit. The limit will give us then information in the vicinity of negative 1 when we can't go there directly and look around. So now what would be the limit as x goes to negative 1 from the left? We don't need to graph it. We don't need to type in numbers close to negative 1 and see. We kind of have our answer, don't we? Yeah, it's negative 2/5. If we know that's a whole, it doesn't matter what the graph looks like. It could look like a snake, something like that. It doesn't matter. What we know then is this. As we approached negative 1, it was approaching negative 2/5. And so regardless of how curvy the road was, we're approaching that from both sides. Okay? That's the general limit theorem. So the limit from the left is negative 2/5. And the limit from the right is negative 2/5. And the general limit is negative 2/5. Right? They're all the same answer. If you know the y value of the whole, you know the answer to all three of those. And it's always going to be the same value. Cool. Now what if, hypothetically, there wasn't a whole there, but there was actually a function value there, and it was continuous? Would that change B, C, or D? No, because whether the bridge is there or not, we know the roads are lining up, and the roads are the limit. It would change this, right? It would make that the same value, and now it would be continuous. We could drive across. So again, the limits can exist independently of the function value. They're not necessarily related, okay? All right, sweet. Comments or questions on that? We're going to talk about vertical asymptotes exclusively at a later time, so I'm not going to mess with what's happening at 4, okay? But right now, the holes are important. You get 0 over 0, or the factor divides out, there's going to be a hole there, okay? We are in here until 2:13. Okay, sweet. All right, so let's say that we have this new goal now in the road, bridge, road analogy. If our goal then is to safely and smoothly drive across a chasm or a canyon in our car with our loved ones, what relationship among the road and the bridge and the road must there be? Well, here's another picture depicting the same thing. And yes, I did this myself in my photo editor of choice, Microsoft Paint. Sweet. Okay. So, of course, we need this. We need the road coming in from the left. Okay. That needs to then be connected right here at the same y value to the bridge, which would be the function value. And that needs to be connected right there to the road going out. Okay. Again, if any one of those three things fails to exist, or any two of them are not equal to each other, they don't sync up, we're not going to be able to safely cross, okay? When those three things then are the same, we say that the function is continuous at that point, which means we could safely drive across. All right, and that brings us to this hugely important definition. We now have a way to determine how a function is quantifiably continuous at a point, other than I can draw it from left to right without lifting my pencil, okay? So here it is. A function is said to be continuous at a point. And when I say point, you can either refer to the ordered pair, or you can just refer to the x value where it's continuous. Either one, okay? If the following things happen. The limit from the left of c is just, again, an arbitrary x value. The limit from the left of the function is equal to f of c. This is the y value. This is the bridge, which is equal to the limit as x approaches that same x value from the right-hand side. Okay? This is sometimes called the three-step definition of continuity at a point. Okay, if you want to think about it this way, the road coming in is equal to the bridge, which is equal to the road going out. Road, bridge, road. Road, bridge, road. When all three of them are the same, and they all exist, the function is continuous at that point. And again, to reiterate, if any one of those three fails to exist, or any two of them are not equal to each other, the function is not continuous at that point, and we cannot drive safely across, all right? So one of the things that you're going to have to do then is to determine, without a graph, without a calculator, if a function is continuous at a point. And you're going to be asked to justify based upon these three things, okay? And so you're going to have to know how to write the terminology. I'll show you what I mean here on example 6. Okay, it says, using the definition of continuity, determine whether the graph of this function is continuous at the following points. And then it says something you'll see quite a bit, justify. So when justify is written there, that means you're going to have to use some kind of mathematical argument. Whereas opposed to if it says explain your reasoning, that's really just words. Okay, so there's going to be some math syntax that you're going to have to use. And the math syntax you're going to have to use here is this stuff up here that I circled. Okay? All right, so they're talking about at 2, 0, and negative 10. Well, notice we have a rational function again. So that's going to be a cubic divided by a quadratic. You know, we don't even need the calculator. We don't need the calculator. Okay. So what should we do first? Factor it, right. Factor it. The bottom is a quadratic, so it's going to have up to 2 discontinuities. So the top, if I factor out an x, I get x squared minus 4. And the bottom should factor nicely. If I give you something to work with, it should factor nicely. Should be x plus 10, x minus 2. Is that completely factored? No. The top can go even more. So h of x, now we have a difference of squares. So x times x minus 2, x plus 2. And the bottom, x plus 10, and x minus 2. All right, let's do ourselves a favor and do what we've been doing. The domain of h is going to be the set of all x such that x is not equal to what values? Negative 10 and positive 2. Good. So those are both discontinuities for sure, which is why you're asked to determine if they're continuous at negative 10 and 2. Okay? Let's see what types they are. Does any factor divide out? Yeah. The x minus 2's divide out. So when you plug a 2 in, you're going to get 0 over 0 because of those factors. So because we can remove them from the equation, it's going to be a removable point discontinuity. So we could say that H has a hole at 2, comma, and then remember to figure out the y value of the hole. We do what? Plug it into what's left, right? Which, let's see, we'll do this together. We got 2 times 4, which is 8, all over 2 plus 10 is 12. So that simplifies to 2/3, okay, for what it's worth. And what type of discontinuity is there then at negative 10? Vertical asymptote, good. That factor doesn't remove. You plug a negative 10 into the top, you don't get 0. So H has a vertical asymptote at x equals negative 10. All right. So that should be enough information then to answer these questions pretty quickly. All right, it says to discuss the continuity at each of these using the 3-step definition at x equals 2. Well, what do we already know about 2? There's a hole. Now, here's what you don't say based on the 3-step definition. You don't say that H is not continuous at 2 because there's a hole at x equals 2. That's a consequence of how based on the 3-step definition. All right, so here's what you do, what I already mentioned. If any one of those 3 fails to exist, or any 2 of them are not equal to each other, that's your justification for it not being continuous based on this definition, okay? So what would be the easiest argument there? The limit from the left equals the limit from the right, correct? But what doesn't exist at 2? The point, the function value. Yeah, so that's going to be the easiest way. Okay, so we'll just say that H is not continuous, and you can abbreviate that like that, and you say at x equals 2. So you write in complete sentences, and that would usually get a check for the correct answer. And then you could say since or because, and simply you could just say since H of 2 equals DNE. If any one of those 3 fail to exist, or if they all exist and any 2 don't equal each other, that's enough justification. So there's a hole there, right? The roads are lining up, but we're still missing the bridge. The limit exists, but the function value doesn't. Okay, what about at 0? It is continuous, right? And we kind of know that because the only place where it's not continuous, based on this, was at negative 10 and 2. So it must be continuous everywhere else. But that's not our argument. Here's what we're going to say. Here's the easiest way to do it. If you want to get your machinery or your notation up and running, you could do this each and every time. You could write the limit as x approaches 0 from the left of h of x equals, and then h of 0, that's the bridge, and then the limit as x goes to 0 from the right-hand side. Okay, so that's basically setting up the proper notation for your road, your bridge, and your road. And if you want to do that each and every time, that's good. And now all you have to do is find those. Well, how are we going to find each of those if we don't know what the graph looks like? We can find h of 0 pretty easily, right, just by plugging in. So each of these factored versions versus the original expanded, they serve a purpose. The top one's probably easier for direct substitution when you plug in a 0. Because if you plug it in the top, you get 0, and the bottom you get negative 20. What's 0 divided by negative 20? 0, right? So I know h of 0 is equal to 0. How am I going to figure out the limits? Well, look at this. If a function is continuous at the point, the limits are equal to the what? The function value, yeah, the point. So because we know in advance that it's continuous there, we know all 3 of those are equal to each other. So as long as you have those labeled like that, you could then say h is continuous at x equals 0. That would get a check. And then the reason would be since. You have to equate all 3 of them, but you don't have to write the syntax over again. All you have to do is say since 0 equals 0 equals 0. You put all 3 of them there. And yes, in fact, 0 does equal itself, but it's not arbitrary, right? So it wouldn't be the same to say since 7 equals 7 equals 7, right? because these zeros refer to these up here, okay? And so that would get the other check. I think we're running out of time, yeah. So, nope, maybe, no, yeah, just, 3 minutes, okay. Let's just finish up here at negative 10, What do we have at negative 10? A VA. So this is kind of getting into what we're going to be talking about more tomorrow. At a vertical asymptote, let's say it lives on one side or both sides, it doesn't matter. There's only two options. The y values either increase without bound to infinity, or they'll turn downwards and they decrease without bound to negative infinity. If I said that you had infinite potential, would that be putting a limit on your potential? Absolutely not. So do you think infinity is a limit? It's not, okay? It's not. By definition, infinity is a never-ending journey going up. There is no limit to how high or low it will go. So the limit's not going to exist there. But we don't even need to cite the limit because what do we know about the function value at negative 10? It doesn't exist. So we can actually use the same argument that we did on part A. We could say h is not continuous at x equals negative 10. That would get a check. And then the reason could be simply since h of negative 10 equals dne. Notice we're not saying because there's a vertical asymptote there. That's not based on the three-step definition. That's a consequence of the fact that the function value doesn't exist, and we'll talk about it tomorrow. Your limits are infinite. Okay? That makes it a vertical asymptote. Okay, so that is a great place to stop. Example 6. There is a worksheet. There's a key posted. Remember, you're not turning it in. But tomorrow we'll quiz on anything up to here. I'll probably have you find the y value of a whole by factoring and plugging in, writing it as a limit, and then 6 or 7 unit circle things, okay? Sound good? And I'll be here in the morning at 8 o'clock if you have any questions.